This video will discuss the thermal energy of atoms and molecules in molecular dynamics. Okay, so the previous video we looked at how some ensemble properties can be calculated. Various properties of a molecule or collection of molecules could be averaged over various configurations. And one of those ways we looked at was called molecular dynamics, where we're averaging the result over a large period of time. So if the system is going to be moving over large periods of time, that implies that our coordinates are going to be displacing from place to place. And if it's directly analogous to moving position over units of time, then that gives us something which is velocity. How much do we move over time? Derivative of position with respect to time. So if we have three n coordinates of our molecule, x1, y1, z1, x2, y2, z2, all the way to xn, yn, zn. So we have 3n coordinates for our n atoms. Then we have 3n velocities as well, because each of these coordinates has a derivative with respect to time. So we have vx1, vy1, vz1, etc. Okay, so typically in the kinds of energy functions we have, our energy functions depend only on position, and they do not depend on time, they do not depend on velocity. So what this means is that these two sets of coordinates and velocities, spatial position and speed, give us the different kinds of energy contributions we have to the total energy. So our coordinates are going to give us our potential energy, our PE. Then our velocities are going to give us our kinetic energy, so the energy of where we are in space and the energy of how fast we're moving. And then kinetic energy plus potential energy gives us our total energy. Okay, so we already know a lot about these energy functions. We've been talking quite a bit about these energy functions in the molecular mechanics chapter and this molecular dynamics chapter. And typically for molecular dynamics, you're going to have some energy function which looks like the kinds of molecular mechanics functions we discussed previously. So we discussed that our potential energy, V, is a function of the set of the coordinates of all atoms, as we just said. And typically that'll come from some kind of molecular mechanics type idea. So we know where we're going to get all of our potential energy from. We know how to, if we're given a specific force field, how to, given the x, y, and z positions of the atoms, calculate what all the bond lengths, bond angles, dihedrals are, interatomic positions are, and calculate the energy there given various parameters. That was the previous chapter. So we know how to get a potential energy given our coordinates. Now the question becomes, what do we do with these velocities? Well, where do we get them from? What do we do with those? So our kinetic energy, well, we know that kinetic energy from general physics is a sum over all of the atoms, 1/2 mv squared. So 1/2 mass of atom I times velocity coordinate I. So for a given atom, the kinetic energy of that atom will be 1/2 m of that atom. So for atom 1, it'll be 1/2 m1 times quantity vx1 squared plus vy1 squared plus vz1 squared. And then each atom has its contribution to the total kinetic energy. All right, so how do we get these kinetic energies? What do we choose for the velocity in the beginning? Okay, so we have to make some kind of arbitrary choice. So some arbitrary choices are better than others. So what can we do? Well, we know that the temperature is proportional to the kinetic energy. Now that's not exact, but I'm hand waving over some things. But in the ideal gas, that's true. In the approximation that the atoms aren't interacting with each other, that would be true. And we're going to use that to get some ideas about what these kinetic energies should be. Okay, so if the kinetic energy is related to the temperature, the velocity is related to, the kinetic energy is related to the square of the velocity. So that means our average velocity, or our average velocity squared, our RMSD velocity, is going to be somewhat related to the square root of temperature. Okay, so how is it going to be related to the square root of temperature? So we know as our temperature gets bigger. If our temperature increases by a factor of 4, our velocity should increase by about a factor of 2. But what is the prefactor here? So if we know this is a proportionality, approximately, but what should this prefactor be in order to get these? Okay, so we'll go back to our old friend, the ideal gas law. PV equals nRT, number of moles times gas constant times temperature. But we know that that also equals number of molecules times Boltzmann factor times temperature. Divide n, or multiply n times Avogadro's number, divide r by Avogadro's number, you've multiplied by 1, and so nr equals nk. All right, so how is this going to be related from there? So we have the relationship that the sum for our n atoms, or our n coordinates if you prefer, 1/2 mi vi squared. Notice that the units of nRT, or the units of nkt, when you multiply those together, those are energy. So Boltzmann factor is joules per Kelvin, temperature is in Kelvin, so this is joules. So pressure times volume is an energy, and the nkt is also an energy. There's no potential energy for an ideal gas, so this is directly related to kinetic energy. All this energy from this temperature is kinetic energy going on. Okay. We know also from the equipartition theorem in statistical mechanics, in classical mechanics, that the energy of these three modes of motion, so we have 3 velocities, each of them is going to have 1/2 kT of energy. So this is going to be 3/2 nkt for however many n atoms we have. Okay, so let's move. So ideal gas law, energy, no potential energy, and equipartition theorem was how we got there. So now let's move this n to the other side. So we're going to have 1 over n, sum I equals 1 to n, 1/2 mi vi squared equals, well, what does this equal first? So we have the velocity of a given, or the kinetic energy of a given atom, summed over all the atoms, divided by the number of atoms. So this is actually the average kinetic energy of a specific atom. So I'd say 1/2 mi vi squared, the average value of that, in the brackets noting expectation value or average value, equals 3/2 kT. I move the n to the other side. Okay, equals 3/2 kT there. So notice there's a factor of 1/2 here. I actually needed a 1/2 in there. Okay, so if I multiply both sides by 1/2, then what I have is that the kinetic energy, or 2 times the kinetic energy, mass times velocity squared, of an atom is equal to about 3 kT. For an ideal gas, that would be true. Okay, now we'll notice that the velocity of an individual atom is equal to, or the velocity squared would be the x component squared plus the y component squared plus the z component squared. So I'd have this as mi times vxi squared plus vyi squared plus vzi squared, the x, y, and z components, is equal to 3 kT. Okay, there's also no reason to assume that the x, y, or z, either of them is special, either of them is a privileged coordinate, they're all equal. So this 3 kT should be separated equally between all 3 of these dimensions here. So there's 3 kT of energy here, and there's 3 different dimensions, x, y, and z. Each of them should have the same average amount of energy in their dimension. So that means that each of these dimensions, so mi times vxi squared, is equal to kT. So if we take that and then we divide by m and we take the square root, we have that the velocity of an individual coordinate of an individual atom is approximately the square root of kT over m, which is fairly similar to the result you get from just the kinetic theory of gases. Okay, so that's where we're coming from there. So we showed that it's proportional to the square root of T to the extent that the atoms aren't interacting. So it's proportional to the square root of T, and the prefactor there would be the square root of K over M. Okay, so that's approximately what our root mean squared velocity component should be there. All right, so our kinetic energy then over time, as the molecule evolves in time, as I said, due to the equal partition theorem, is going to be distributed between our different modes. So our energy is going to be distributed equally in the end between 3 translations, 3 rotations, or 2 if it's a linear molecule, and 3n minus 6 vibrations, or 3n minus 5 if it's linear. Okay, so these translations, the kinetic energy of a given molecule, the rotations, the rotating of a molecule, and the 3n minus 6 vibrations of a given molecule, all of those are going to have, each of those modes will have on average 1/2 kT of energy each. So is the individual velocity components of the atoms given this type of distribution will eventually equally distribute themselves on average between these different modes there. So when we're talking about molecular dynamics, we have to assign some type of initial velocity to the system. And our choice of initial velocity is going to be informed by this type of logic, that the temperature has this relationship to the velocity components of the atoms based off their masses and the value of the Boltzmann factor.